This video is about Newton's law of gravitation. We'll start by learning the basics of this law, and then we'll look at the link between gravity and orbits. Let's begin with the basics. The basic key concept here is that objects exert a force on each other because of their mass. For example, the Earth exerts a force on us, and this is the reason why we don't simply float off the surface of this beautiful planet. Of course, according to Newton's third law of motion, we also exert a force on Earth. The force in this example is called the gravitational force. Let's see what properties of this gravitational force were discovered by Newton. He established that the gravitational force between two objects is always attractive, that it is proportional to the mass of the objects, and that it is inversely proportional to the square of the distance between the objects. Therefore, if we have 2 point masses, m1 and m2, where the distance between the masses is r, we can summarize the above statement by writing that F, the gravitational force, is proportional to m1 times m2 divided by r squared. As you can see, Newton's law of gravitation is one of the inverse square laws in physics. Another inverse square law that we learn about in this course is Coulomb's law. To express Newton's law of gravitation in equation form, we need to introduce a constant. Doing so, we get the following formula, which contains these variables. Uppercase G, the constant that we introduced, is called the gravitational constant, and its value was established through experiments. This value is provided in your data booklet. Now that we understand the basics of Newton's law of gravitation, we'll move on to explore the link between gravity and orbits. Let's take a satellite that is orbiting a planet in a circular orbit. We'll denote the mass of the satellite as lowercase m, the mass of the planet as uppercase m, and the distance between the satellite and the center of the planet as r. We'll also assume that the satellite is orbiting at a constant speed v. Now, since the satellite is moving in a circle at constant speed, there must be a centripetal force on the satellite. The direction of the centripetal force is towards the center of the circle, so towards the center of the planet. The key concept here is that this centripetal force is provided by, so equal to, the gravitational force exerted by the planet on the satellite. Therefore, we can write that the gravitational force is equal to the centripetal force. Now, based on the formula that we just learned for the gravitational force, on the left-hand side we get G times uppercase m times lowercase m divided by r squared. Based on what we learned about the centripetal force in topic A, on the right-hand side of the equation, we get mv squared over r. We use lowercase m here because FCP is the centripetal force on the satellite. So this is the equation that links gravity and orbits. The speed of the satellite, so v, is called the orbital speed. Working further to find v, we can simplify by m and by r, so we end up with the following equation. V squared is equal to g times uppercase m divided by r. From here, v is simply equal to g times uppercase m over r under the square root. As we already mentioned, v is called orbital speed. Finally, let's derive an important formula linking orbital period and orbital radius. We learned in topic A that v, the speed of an object moving in a circle, is equal to 2 pi times the radius of the circle divided by the time period of the circular motion, which is the time it takes for an object to complete one full revolution. You can see from our working in the purple text that v squared is equal to g times uppercase m divided by r. Now if we square 2 pi r over t, we get 4 pi squared r squared over t squared, and as this is an expression for v squared, we can equate this to get gm over r. Rearranging gives us that t squared is equal to 4 pi squared r cubed divided by gm. Applying this expression for a satellite that is orbiting a planet in a circular orbit, t is the orbital period, r is the distance between the satellite and the center of the planet, and m is the mass of the planet. As you'll see later, this formula expresses Kepler's third law for a circular orbit. With this conclusion, we have completed our learning about Newton's law of gravitation.